So scientists start to think about how probable reactions will be. Like, how probable is it that reactants will go to products, i.e., how probable is it to be spontaneous? And probability plays a big part of the science of thermodynamics. So probability suggests for the reactions which are going to occur, the product favored reaction, if you have a reaction that's going to occur, it's going to result in dispersal. And the dispersal, which is basically concentrated to less concentrated, dispersal can be of energy. So you start with a concentrated energy source and it becomes more dilute after a while. You could have matter dispersal, so all the matter is nice and organized, and after it's done, it's all over the place. And you can even have dispersal of both energy and matter. So what this is saying, and Boltzmann, by the way, was the one that kind of figured this all out. What this is saying is that when you look at all reactions that are known, the probability that a reaction will happen is much, much, much higher if you have dispersal. And it can be energy, like an exothermic reaction. It can be matter, so you go from concentrated matter to more dispersed matter, or you can have the dispersal of both energy and matter. So Boltzmann was the one that kind of formalized all of this and opened the door to it, and we'll see what the results of this are in just a little bit.
Consider a pair of flasks, one containing gas molecules, the other completely empty. If the flasks are connected at their mouths, gas in the filled flask will move spontaneously to the empty flask by its molecular motions. Eventually, the distribution of molecules will be even throughout the flasks. The final state in which the matter is more dispersed is much more probable than the initial undispersed state.
This is an example of matter dispersal. You have two flasks. One's essentially a vacuum and the other one has a gas inside. And if you open the little stopcock between the two sides, it makes sense that the side that's more concentrated, a lot of that matter will go through to the vacuum side, and at the very end then you'll have an even distribution of matter. So matter has been dispersed. It was in a very concentrated form. It was on the left side, and at the end it's very well dispersed over both sides, like you have an even distribution. That's what they mean by matter dispersal.
Stored chemical potential energy is released from reactant molecules in an exothermic reaction. This energy spreads out or disperses over the product molecules and the molecules in the surroundings.
A lot of reactant molecules have a lot of potential energy in them, if you will, and when they react, that potential energy is turned into kinetic energy. It's released as an energy dispersal wave, if you will. So the energy then goes to the surrounding molecules, usually like the solvent, water, or even possibly the air that it's around. But those molecules around the reactants then end up with more energy. So this is energy dispersal. It was like maybe in just a molecule or two, and now it's been distributed over more molecules, like more solvent molecules, stuff like that. So if you have a reaction which can disperse the matter and or disperse the energy, it's much more likely to occur than if you don't have one of those options possible. So here's a question that you might see. It says, which process represents matter dispersal? Okay, and so here's just some possible ones, and let's go through them and talk about them. So first of all, it says cleaning your messy room. Well, your messy room has stuff all over your room, we'll say, and as you put it away, you're putting them into drawers and shelves and stuff like that. So the matter was dispersed over your whole room, and now it's less dispersed. It's actually more concentrated as you clean it up. So that's certainly not matter dispersal. That would be the opposite. You're having the matter become more concentrated. Second one, condensing gaseous water. As you go from a gas to a liquid or a liquid to a solid, you are definitely making the molecules closer together. The intermolecular forces, as we talked about in the last Chem 222 class, the intermolecular forces begin to kick in. It holds them all tighter. So going from gases to liquids is certainly not matter dispersal. You're actually concentrating the atoms a little closer. So gases to liquids, liquids to solids, those do not result in matter dispersal. It would be the opposite, actually, of that. C, crystallizing a solid from a solution. So again, the solid was distributed all throughout the solution, but you're getting rid of the solvent and able to make the solid form again. That's really concentrated your solid. That's like cleaning your room in some ways. So that is not matter dispersal either. However, the next one, eating dinner, all right, you start with whatever foods you like to eat. You eat them, the energy goes throughout your body, but more importantly, the food that you eat is obviously changed in your body. It's changed into waste and sugars and all those kind of things. So definitely eating things is a source of matter dispersal, all right? You're having a lot of concentrated matter in whatever food you eat go through your body. It's broken down into wastes and CO2 and all that kind of stuff. That's definitely matter dispersal. Real fast, you're forming ammonium dichromate from water into chromium 3 oxide. Notice you have three things going to one thing: water, nitrogen, and chromium 3 oxide going to ammonium dichromate. That's definitely concentrating your matter. You're going from lots of moles to essentially a single mole. That's going to be definitely not matter dispersal either. So the only one on there that's matter dispersal would be D. As you eat and drink things, the stuff in them goes through your body. That's definitely distributing the matter throughout your body in different ways. You're not going to get it back at the end of the day, shall we say. Yeah, there's lots of examples of this stuff all around us. So the directionality of reactions is important. The energy dispersal part is pretty cool. So when we have an exothermic reaction, that stored energy is released. All of those are exhibiting energy dispersal, all right? Concentrated energy going to the outside, warming up the solvent molecules or gas molecules, whatever you have around it. So exothermic reactions are definitely going to exhibit energy dispersal. And that's why most of the time those are good examples of reactions which will occur. That stored potential energy just starts in a few molecules, the reactants, but then it finally ends up over quite a few molecules. Like the solvent is usually what happens, but sometimes you could have the gas, the air over the reaction mixture, but it goes from just a few molecules to a lot of them. So when you have that energy dispersed at the end, it's more probable. And so usually exothermic reactions are product favored. But you'll notice there that I'm kind of hawing and hemming. I'm saying usually. Good old Boltzmann there realized that, something must be going on here. This is an example of an exothermic reaction. There's no sound to this video, but in this reaction, which is called the thermite reaction, iron 3 oxide is reacting with aluminum to make iron metal and aluminum 3 oxide. And notice that delta H there, it's a negative number. That means exothermic. And this reaction is incredibly exothermic. Sometimes they use this for explosives in the military. It gives off a lot of energy. And so anyway, yeah, thermite is definitely, and you can see this reaction happens. It's definitely happening. You can watch it there. It's kind of cool, right? So this is spontaneous. So here, exothermic means spontaneous. It means it's going to occur, and it does.
In the center beaker is water at room temperature. To this we add solid ammonium nitrate. The ammonium nitrate dissolves. Usually, a reaction that occurs so readily is exothermic, but we see from the thermometer that this reaction is endothermic. The temperature of the water drops significantly. This reaction is not favored energetically, yet it still occurs.
If you've ever had a sports injury, sometimes they say to apply like a cold pack to the injured area. And this is an example of a reaction that creates like a cold feeling. And in terms of delta H enthalpy, that means this reaction is endothermic. And they're very common. Cold packs are great if you've had injuries. What's happening in a lot of them is ammonium nitrate, a solid, all right, is basically turning to a dissolved ammonium nitrate. And in that video, you could actually watch it happen. But what's really interesting here is that the temperature went down. And if the temperature of the system goes down, or the surroundings would be a better way to say it, if the temperature of the surroundings decreased, that means you have a positive delta H. It's an endothermic reaction. So this is an example, though, of an endothermic reaction which occurs, all right? It's not as exciting as thermite, thermite by any means, but you can feel the cold happen. This is a spontaneous reaction. So why this is a good contrast there to thermite, this isn't as exciting of a reaction by any means, but these are both spontaneous reactions. They both occur, all right? The one on the left is exothermic, and generally exothermic means spontaneous. But on the right, we have an endothermic reaction which occurs, and that's spontaneous as well. So what this means is we need more than just delta H to predict if a reaction is spontaneous, to predict if the reaction will occur. And that's what we're going to be exploring in this chapter. So get ready, enthalpy. You're going to have a competitor here in a little bit. Let's see what that competitor is.